All right, guys, welcome to another episode of CUDA Education. I'm your host, Nicholas Main. Please visit CUDAeducation.com. That's CUDAEDUCATION.com. And also subscribe to my YouTube channel. Today, what I want to do is have a quick overview of parallel reduction and specifically parallel reduction in CUDA or using CUDA to do it. Um, it's not a complicated thing, but if you're not familiar with how parallel programming works, it might take you some time to really digest the code and everything that is involved in making it happen. Now, first of all, in order for me to understand how it works and to sort of get everything straightened out in my head and all that stuff, I have to give a shout out to Professional CUDA C Programming by John Chen and Max Grossman. I highly recommend you guys buy the book because it tremendously helped me to understand CUDA programming and just basic operations of CUDA and why things get done. So a big credit and shout out to Professional CUDA C Programming by John Chen and Max Grossman. You could purchase the book using the link here that you could get when you go to CUDAeducation.com. Okay, so this code is, just as a disclaimer, this code is just for educational purposes only. Please don't use it in a commercial setting. I will not be held liable for any losses or damages occurring from the use of this code in any means. Real quickly, I'm running a Windows environment, as you could see here, CUDA Toolkit 9, Visual Studio 2017 Community Edition. I have a NVIDIA GeForce 1050 Ti graphics card. Okay. Now, before we get into code, I think the best way to really get you to understand what's going on is to just show you a graphical representation of what's happening. So what I will do is I will bring over my friend right here, and you will sort of see the big picture, if you will. Okay, so let me adjust this bad boy a little bit for you so you get an idea of what's going on. Okay, all right. So this is a picture that you could get on CUDAeducation.com/CUDA tutorial. And basically what it is it's an array of numbers, right, in one array, in one variable. And you basically want to add up all the numbers in the array and get a single value, right? So let's say you had 1, 2, 3, and 4 in an array, right? So 1, 2, 3, and 4 in an array. So 1 and 2 is 3, 3 and 3 is 6, and 6 and 4 is 10. So you get basically you get the number 10 as your final value of adding up all those numbers in your array. Well, this situation here is the same concept. So we got all these digits, and in each iteration, we're basically trying to combine the numbers to basically boil down to one number, right? Now, notice in the first iteration that you have the first digit, and then it takes in the second digit, and it adds the 2 to get its child number, right? So thread 0 does this, right? And then thread 2 adds up 8 and -1, which you get 7. Thread 4 adds 0 and -2 to get -2, etc., etc., etc. So each one of these values here is represented by a CUDA thread. Okay? So we go from thread 0 to, in our case, 20 million threads, right? So thread 0, thread 1, thread 2, all the way up to 20 million threads minus 1, because of course we have a thread called 0. So it's not the 20 millionth thread, it's the 20 millionth thread minus 1, right? That would give us 20 million of these guys. Okay, so each one of the threads are assigned to a value in the array. Now, what happens is that in each iteration of, or in each loop of the code, it's basically taking a number and then taking the number beside it and adding it up, right? So notice here, thread 0 takes 10 and 1, adds it up, and you get 11. Okay? Now, once you get 11, after the first iteration, we go to the second iteration. So in the second iteration, we take 11 and we combine it with the next value after the previously added one. So in this case, it's now 7, and we combine it to get 18, right? So that's in the second iteration. The third iteration, we do the same thing, but now we're skipping to this element in the array, right? And we're combining 18 and 6, and we get 24. The next one, we do 24, 17, right? And we get 41. So when all these iterations are done, we basically boil down to one number, right? And all these digits will gradually be combined into the thread 0 operation to get you a number, right? Now, notice one thing. Once an element has been consumed by thread 0, or been consumed at all, that the element in that array, in the array, doesn't change. So it's been consumed here, and you get 11, and notice that 1 just stays the same, right? Now, notice that this guy, it started at 0, then an operation was done, it went to 2, then another operation was done, then it went to 6, and then as soon as thread 0 consumes it, and you get 24 here, that it doesn't change again. What this is saying is that as soon as thread 0 consumes the value in that field, the value in that field is no longer useful, because there's no more operations that needs to be done. It's already been included in thread 0, so it just stays the same. So if we look at, for example, this guy, it went from -2 to -5 to 4 to 17, and then as soon as it hit 17, it didn't change again, right? Because thread 0 consumed that value, and thread 0 is sort of your master value, right? So this is sort of what we're trying to achieve in the code. In normal C# or C++ code, on the CPU side, it would simply be you're doing a for loop along all of these integers, right? So you do this plus this plus this plus this plus this plus this, and it's just one for loop, one thread doing one for loop. But in parallel computing, it's all threads sort of managing the processing all at once. And instead of one thread having to loop through each one 20 million times, you sort of have all threads helping in the process until it basically collapses into thread 0, then it basically stops, right? So notice that every time we go, 10 and 1 beside it, then we have to do like a stride, and then we have to go to 7, which is this guy. Then we go to the next stride and we do 6. Then we go to the next stride and then we do 17 over here. So just keep in mind that we have to calculate a stride after each iteration, okay? Because this guy, you don't want on the next iteration is adding back 1 again, because we've already done that. It's doing 7 here, and then it's doing 6 over here, and then XYZ. And also all these other guys also have to continue processing, right? So just understand that there has to be some sort of step or stride that needs to be done. That's the first thing. The next thing that you have to understand is that when after the first iteration, the processing of the program has to make sure that all of the threads in the first iteration are done before you move to the next iteration. What do I mean by that? So you see here how we did 10 plus 1 is 11, right? And then right after that we did 11 plus 7 is 18, right? You have to make sure that once you're finished with this iteration, let's say we're just talking about thread 0. Once you're finished with this iteration, that you don't start processing this value plus the value here before this operation is done. So let's say, for example, I said, okay, I'm not going to sync up all these threads. I'm not going to wait until all of these guys have finished processing, right? I'm not going to wait until everything. I'm just going to, I care about thread 0. Thread 0 is supposed to have my final answer, and all I'm going to do is just run through thread 0, and I don't care with if everything else here is done. Guess what happens? You do 10 plus 1, you get 11, but then you do 11 plus not 7, you do 11 plus 8, because of course you haven't made sure that this operation has finished before proceeding. So you do 11 plus 8, and instead of 18 you get 19. Now here, let's say thread 0 is just super fast, and it's way faster than every other thread in the array. So then now 18, so you get 19 here, because we're doing 11 plus 8, so you get 19 here. It's a wrong answer, which means that your whole operation is wrong. But then you do 19 here, and then you don't even do 19 plus 6. You maybe do 19 plus -2, or you do 19 plus 0, and then you get either 19 here, or you get 12, or what have you. Or you get 19, or you get 17 or something here, right? So basically, because you haven't waited till everything else has finished, your numbers are going to be off. So there's going to be an important part of the code where I'm going to say sync threads. And all that means is that before we go to the next iteration here, I make sure that every one of these guys have finished their operation, and we get correct values for these guys, right? So that when the next operation happens, I'm adding in right values, or good values, or correct values, right? Now, this is very, sync threads is it slows up performance, it slows up processing, because of course you have to wait for everyone else to done before you go to the next iteration. But what it ensures is accuracy. Now, there are two extremes of the spectrum. There's doing sync threads too much, and maybe you do it too much to the point where it's not necessary, and you really slow down your code, or you do sync threads too little, and your code is moving blazingly fast, but your values are wrong, right? Your program is basically random, right? And you get a wrong answer for your calculation, which means that, whatever it is the purpose of your program is, it's spitting out erroneous values, right? So the purpose of CUDA is speed. I discussed that in a previous video. That's the reason why we do it. And we're all concerned about speed, but you have to use sync threads to make sure that your values, the landed value here has been calculated before you start putting it in. The landed value here has been calculated before you start putting in. The landed value here has been calculated before you start putting this guy in, right? So that's my lecture on sync threads. Okay, you have to respect syncing up all your threads before going to the next iteration. Also remember that when you're running a CUDA kernel, when you're running your CUDA code, you know, threads don't necessarily process in sequence. So I can't necessarily guarantee that thread 0 is going to be processed before thread 2, or that thread 2 is going to be processed before thread 12. We might have a pattern of 8, 14, 4, 8, 10, 0 thread. That might be the pattern of how all these things done. So the only way you could get some sort of sanity check in all of this is to do a sync threads to say, okay, all of you guys have finished adding up your values. Now we can go to the next processing, right? And that's basically what parallel reduction or reduction in CUDA is all about. It's about assigning threads to each digit, right? Using each thread to add values, right? Making sure that before you go to the next iteration, that the values have all been calculated for each one of the integers or each one of the threads, right? And calculating a stride. The stride is probably going to be the most, you know, just the most involved thing that you would have to deal with, right? You have to make sure the stride is calculated properly. And we get a value on thread 0, and that's going to be not our final result, but it's going to be the result for the specific block. Now, I don't want to get too deep into this because I'm going to confuse you guys, and you guys like short videos, right? So I don't want to get too involved. But remember that CUDA kernels run in blocks, right? And in each block you have thread 0 within the block, right? So you're going to have many blocks with a thread 0 in them. So what happens is that for a specific block, all the values in that section of the array are going to collapse to thread 0, and you're going to get a final answer on thread 0, right? Now, what we do is that we take all those values from thread 0 from all of the blocks, and then we push it back to the CPU, and then we have the CPU do a simple for loop and add up all the final numbers from each of the blocks, and then you get your final answer. Okay? I hope I didn't lose you, but that's just how it is. We don't have one big block with 20 million threads. No, there's a limit to the number of threads that can happen in each block, and actually it's 1024 is the limit on my card. By the time you're seeing this in 10 years, it might be more, but it's 1024 threads in each block. Okay, so we have to collapse all those values down for each of the blocks and then add up all those values. But we're going to add up the final values. We're going to do the collapsing in the GPU, in the NVIDIA graphics card, but then we're going to push those values over to the CPU, and we're going to have all the CPU add up all the values from the blocks, okay? And we get our final answer. Now, also note that the code has to also do a check. So it has to check and make sure that the numbers that we're calculating from the GPU, or the final answer we get from the GPU, or when we do the GPU processing, matches the CPU result, right? And the CPU implementation is a simple for loop, and it's pretty simple and straightforward. But we want to make sure that the numbers match, just so that we have a sanity check. Because when you have 20 million integers, you can't possibly know just by looking at the numbers that it's actually right. So we do a CPU check to make sure that it's right. Now, this particular implementation of the GPU, of the parallel processing of the CUDA code or whatever, it's a very basic. It's for teaching purposes, and as a result, it's probably not as fast as the simple CPU addition that we do. The for loop on the CPU. It's probably not as fast. But through optimization, through memory management, through optimizing the number of threads in the block, redefining, how the processing of the code is done, you actually get a much faster result on the GPU. But we're not going to do that because we're just starting out and we're just trying to find our way around CUDA, right? So this implementation probably is going to be slower than the CPU implementation, but again, it's just for training purposes, just to get your hands dirty in CUDA programming and all the things it can do. But always remember that the purpose of CUDA is speed. So naturally, you're going to want to learn how to make your program faster, so it takes advantage of all of the parallel processing that CUDA has to offer, right? But there are many different things that you have to tweak in order to do that. But anyway, I'm done talking about that. We're at minute 22 and you guys are already falling asleep. What can I do? All right, so now what we're gonna do is just basically go over the code that I have, and I'm gonna kind of be very brief and hasty through it because it's heavily commented, and you guys can plow through it on your own. Okay. So I already discussed the environment and all the good stuff. Remember, guys, if you have a question, you could either comment on the video, check me on Twitter, YouTube channel, anything you want to do. Okay, but I would say either Twitter or commenting on the YouTube video are the best. All right, so all C# programs start with main. Okay, so we're gonna do that here. So you basically assign a value for your device 0, because I only have one device on my computer, and then you set the device to use, which is the first device and the only device I have on my computer for CUDA. Now you set your size of your array. In this case, it's 20 million, right? Print out the size of the array in the command prompt just to make sure it happens. Actually, you know what? Let me run the code so you guys see what we're working towards. So array size of 20 million. CUDA education grid. So it's a basically 78,000 blocks are in my grid, and there's 256 threads in each block. So 78,000 blocks in my grid, 256 threads in my block. Okay. Device elapsed time 114 milliseconds. The final answer is this guy, and the device result matches host result. So this basically is our mathematical check to make sure that the computer, the CPU processing, and what I calculated using the GPU processing matches up, right? Press any key to continue, and I'm done. So, this is basically your first introduction to, my to what we're trying to achieve. Okay, so now you're not just shooting in the dark. Okay, so the device, set the device 20 million array, print out the array size as you saw in the command prompt. How many threads in each block? 256. You saw that printed out. Right, you saw that printed out here, and yeah, and then so yeah, we set up the timer to figure out how long it takes to process. You could visit this website to get more of an explanation. I'm not going to go through it now because yeah. So we create variables for the CUDA launch. This explains the whole thing, but basically you're using DIM3 variables, right? So you declare block variable or you know, and basically it's declaring how many threads are in each block. And then this basically is a calculated value of how many blocks you're going to need. So remember now, the number of blocks we need is dependent on how many threads are in each block and how many, and then that determines the number of blocks we need. So basically we need 20 million threads, and we need the number of blocks and stuff to accommodate 20 million threads, right? And you could do the math if you want. 256 times this guy, and you should get somewhere around 20 million. Okay, I'm not going to do it right now for expediency purposes. Right, so you calculate that, and then we print out our result, which is basically this guy right here, right? And those are the variables for the CUDA launch. Then we do some memory management. Now, there's a size of integer, and we have to remember each 20 million element is an integer. So we basically take the size of an integer in memory, times it by the size of the array, and we save that as, you know, a memory block. And then we initialize a variable on the host side to hold data that we will send to the GPU. So this is basically the variable, and we're assigning memory to we're basically setting up a bucket on the host side that we're gonna send that holds the data, and then we're gonna send it to the GPU, right? We also have to initialize a variable on the host side to receive data back from the device. So remember I said that each one of those blocks are gonna have thread 0, which the numbers are gonna collapse into thread 0, right? But then initialize a variable on the host side to receive data returned from the device. So each one of those thread 0 values we're gonna have to accommodate or receive back from the device. And notice that it is assuming one integer value for each block. Remember, CUDA Education Grid holds a number of blocks. So basically, this is basically saying, you know, we're gonna receive data back from the host, and we have to make sure the memory size, which is just it's one for each block, right? One integer for each block is prepared for it. So this is all memory management stuff on the host side. Initialize a variable on the host side that will hold our final answer. This should be a number, not an array. So when we get the thread 0 result from each block, we're gonna have to do a for loop on the CPU side, on the host side, to add up all those numbers. And when we add up those numbers, we're gonna get a value. And that value is gonna be a number, it's not gonna be an array. So host variable final sum of block totals from GPU, right? That's all this is. And memory management, okay? Now we have to actually create the numbers that are going to go into our array. So I only said that there was an array and that there were 20 million integers in the array, but I haven't told you what those numbers are. So here is my very quick creation of all the numbers in the array. So it's a simple C++ for loop, C# for loop, right? 0 to size of the array 20 million, loop through them and create a random integer and put in our in our variable. Now you could print out the numbers if you want, but because it's 20 million, you would be there all day, and you don't want to do that when you have 20 million. But let's say you change my array size. Remember, my array size is up this guy. Let's say you change my array size to 5. Let's say you change this to 5, right? Then you could print out the values here if you want and just follow it through for yourself. But because I'm doing 20 million, I'm commenting it out. Okay? Now I've created my array, so I could actually do a quick accuracy check on the CPU side. So add up all the numbers of the array on the host side, on the CPU side, and get a number, right? So that's basically all I do. CPU addition result is 0. I do another loop, and I say current results plus the next results, just add it all up and give me a final. Okay, so I put that in my back pocket. It's just there for safekeeping, so when I get a result from my GPU operation, I could compare it. Okay, nothing crazy. Now we're doing memory management again. I thought we did memory management already. Yeah, but we're doing memory management again for the GPU or for the device, right? So notice that we're performing these actions on the host, but it's sort of for the GPU. So we're performing it on the CPU, but it's really doing stuff on the GPU, right? On the host side. So initialize a variable that will hold data received from the host. So device data received from the host. I initialize it to null. And then initialize a variable that will hold data to send back to the host. So that's this guy. Again, it's null, right? So we do allocate memory. Notice that we use the keyword CUDA malloc. So in C++, C#, what have you, you do malloc. Well, for the GPU, you do CUDA malloc, right? And you basically do the same thing. Remember our friend int bytes, because we're talking about 20 million bytes. 20 million integers, so we do the int bytes thing. Right, so we do the same thing for device data received from host, device data sent back to the host. We basically do the memory operation again, but notice that it's based on the number of blocks that we're dealing with, right? So this guy, and we do CUDA malloc again, okay? Not gonna get into it, but you could read up on CUDA malloc if you want, but that's basically the memory management for the GPU or the device, whichever word you like to use. So then we do a transfer data operation. The source, the destination, the source, the space required for the operation, and the direction. Not gonna get too much into it, but CUDA mem copy is a memory transfer function. So we got the destination, source, size, memory size, and the direction. So it's CUDA mem copy host to device. Okay, host to device. Remember that we're transferring stuff from the host and we're carrying it over to the device. We do a CUDA synchronize, make sure all preceding tasks on the GPU has been completed before processing, right? So that's just a sanity check, basically. Don't mix up stuff. CUDA event record, this is the timing thing. Not going to get into it, but it's the timing thing, okay? So we launch a CUDA. Remember, you could always check the website to figure out all that stuff. Launch a CUDA kernel. So right, this is our CUDA kernel here. And we're putting in parameters. So we put in the number of blocks and the number of threads per block, basically, right? Number of blocks, threads per block. And then we pass parameters. So device data received from host, device data sent back to host, my array size, and what have you. This is a timing thing again. So normally when a kernel is launched, the CPU on the host side, on the CPU side, continues processing. So it would launch a kernel and the GPU would start spinning its wheels, but then it will continue processing, right? But right, remember by default, the GPU will launch the kernel and immediately continue processing. We use CUDA device synchronize to tell you the CPU to halt further processing until the CUDA kernel has finished doing its business. Yes. So we're not going to start processing things down here until this guy has finished, right? Now, in other instances, when you have code where you don't necessarily need to wait for the kernel to finish, you could not have this and just continue about your business on the CPU side. But for our purposes, we need this to be concluded before we can continue. So I just wanted to note it for you to understand that what this was about. And then now we're going to go to the kernel and just see what's going on up there. So the kernel is all the way up here. So notice for the GPU, we use this global thing to demarcate. We could also have used device, but global just works better. Global, I think, generally means that the CPU and the GPU can call it, but so maybe device would have been better, but I use global, right? So this is our kernel, and then these are all the parameters that we passed in. Okay, so I want to get the thread ID of the particular thing that's processing. Now, remember, this is not, how do I say this? This is not necessarily a for loop when this is being launched. It's like all the threads are lined up, all 20 million of them, and bang, they all process this thing at the same time. Okay, so it's not like we're doing a for loop with this function or anything like that. It's all 20 million threads are being pushed through this function, right? So, but it's being partitioned, not partitioned, but it's being this thread ID is basically on a per block basis. Thread ID x.x, it's a built-in NVIDIA CUDA variable that tells you what thread in the block is currently processing, right? It's something the NVIDIA gods invented and gave to us, right? So we know what thread is being processed, and basically I just assign it to a variable so that I know what thread I'm dealing with, right, in the processing. Now I need to know I know it's thread 0, for example, but I need to know in the bigger scheme of things which literal thread is it in the 20 million group of threads. So remember, thread 0 is on the per block basis, but then I want to know in all the 20 million threads that are out there, where does this thread land? So that's where this calculation comes into play. Not going to get too much into it, guys. You could visit this website if you want to know more about the calculation, but you you want to know in the 20 million sea of threads, where does my thread land? So it might be thread 0 of block 1, or it might be thread 0 of block 20,000, or block 10, or block 5, or block 100. I don't know. So this guy gives you sort of the big picture address of it. Okay. Convert global pointer to the local pointer of this block. Okay. Not gonna get into it. Now we do a boundary check to make sure that the threads that are processing the array is not greater than the size of the array. So this is just to make sure that, like, thread, let's say for example there's thread 20, the 21 million thread doesn't process or do anything. We don't want the 21 million thread to do anything because it's not necessary. I don't want it to take up compute resources or anything. So if for example you're talking about the 21 million thread, you just return, because we don't need you and we have no business with you. Okay, so that's what this guy is, just a boundary check. Okay, so then now we start doing this the for loop. Now this for loop, it's not it's for each of the threads that are running. So it's not like one for loop where it's one thread that's going over 20 million times necessarily. What it is each of the 20 million threads has to basically process through this for loop. Now, when we say for loop here, we basically mean this guy. So this is one iteration, or this is one iteration. This is the next iteration. This is the next iteration. And then this is the next iteration. I don't know if I lined it up properly, but basically it's all of the threads that are looping through the matrix, or through the array. Okay, so that's really what the for loop is saying. Remember, all these guys these are the numbers, but these are the threads that are doing the work. So we're saying, okay, this is iteration 1, where we get results here, then iteration 2, where we get results here, then iteration 3. So it's all of these threads that are being processed where it needs to be processed in order to collapse down to thread 0, right? So that's sort of what this for loop, and remember I kept talking about the stride. This is the stride that determines what's the next value that we tackle. Okay, so right, that sort of dictates where next you go to add the value, right? Not gonna get too deep into it, but if you follow the code, you would really get a grasp of what's going on. And notice here we do the modulus 0, because if it's not, if we don't need to process it, we're not going to, right? So that's sort of this is sort of the heart of the code. Calculate the sum of the current value in the array at index and the value in the array at index that plus 1. So the current value plus the value at the stride, right? So that's basically talking about current value plus the value at the stride, right? Value at the stride. Current value plus the value at the stride. Value at the stride. So that changes. But again, notice that you wanna know what the stride is, right? But you also want to know, so you want to know what the stride is, right? But you also want to know So this is the stride right here. This is a stride right here. But you also want to activate or deactivate certain threads, right? So this if statement makes sure that only certain threads actually process this stuff, because we kind of deactivate threads when they don't follow this this rule. So this calculates sort of the stride, and then this activates or deactivates certain threads, right? And then we do that plus the stride, right? Now remember I keep talking about sync threads. Notice see how much text I have for sync threads? Yeah. The reason I do that is because we have to make sure that all these guys have calculated before we go to the next step. So all these guys have to be calculated, right? All these guys has to be calculated, all these guys has to be calculated before we tackle the next step, right? Which is here. That's all sync threads is doing. But notice how I have so much explanation, and you guys can read it on your own to figure out what's going on. So then, so once notice the for loop is right. Notice the for loop is here and here. So remember, the for loop is basically looping through all these guys here, right? Bang, 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 right? So once we basically collapse down to the value at thread 0 for each block, at this point, all the processing within the block has been concluded, and now you can proceed to recording the final value in the master list. Write the value of the block to global memory. So this for loop is basically on a per block basis. So we're doing this for loop for each block, right? Now, in our case, remember we had 78,000 blocks, okay? So we're doing the for loop on a per block basis, and we're collapsing down to thread 0 within the block. Once we collapse down to thread 0 within the block, we basically record that value in the master list. And this master list is data to send back to host, right? And you notice how it's local data of block and then 0, right? So we're doing it for each particular block, right? So block 0, block 1, block 2, block 72,000, block 78,124 or 125, block 78,120, block 75,000, block 69,000, right? So we're doing it for each one of the blocks, right? And we're recording the thread 0 value in our data to send back to host variable, right? So this guy should have about 78,125 elements in its array. This is an array, and it's going to have 78,125 integers or elements in it, okay? Because we're doing it for each block, okay? And that's all that is. So let's go back down to right, let's get back down to our kernel. So this guy basically is saying, it's finished processing, and then now we're finished processing on the kernel. We've created our master list, and then we can proceed. This is just, again, timer, which I'm not going to get into. Right, so you print out the number of time it took the kernel to run, even though technically we just calculated the kernel and not necessarily the very final step, but that's okay. We get a number, right? This is just for the GPU kernel to run. So at this point, the final block numbers from the summation within each block has been completed and are waiting to be transferred from the device GPU to the host. Please note that this is not our answer yet, as we have to add up the numbers from each block to get our final answer. We will do the last addition on the host side. So copy block numbers from the device GPU to the host. CUDA memcopy. So now we're doing the memcopy function again. Our destination is host data received from device. That's our destination. Our source, where we're getting the data from, is device data send back to host. Notice that this variable is the same as this variable, right? Because this is our variable with the master list, right? And then we have to also take into consideration what's the memory size of this operation. Well, we know the number of blocks is 78,125, right? This guy, that's the number of blocks. So we do that guy, 78,000 whatever, times the number, an integer, how much memory space each integer takes, and that should be the size of this guy. And then of course we do the CUDA memcopy thing here, but notice now we're doing device to host. The first time around we did host to device, but this time we're doing device to host because we're taking information from the device and we're moving it over to the host, right? That's what the memcopy thing. So you have to make sure you put in the right direction that the operation is going. Okay. So you initialize a variable to hold our final answer. It was already initialized above, but I repeat it here just for clarity. So now I just create another, or re-initialize the same variable. Host variable final sum of block totals from GPU. So I just initialize it to 0. Okay, so then I do a simple for loop in C# that loops through each block. It loops through each of the values that we got from the blocks, and it should be 78,000 of them, and we basically loop through them. Right, host data received from device, which was this guy right here, and we add it up to get a number. Print our final answer, the number of blocks used and the number of threads in each block. So device final answer is blah. Of course, I have to do a plug because I'm a shameless promoter. And then we do the actual answer here, right? And that's this guy. Final answer is this, subscribe to whatever, and then we do accuracy check. Check if the result from the device matches the result from the host. So we basically say if the host variable final sum of block totals from GPU, which is this guy, whatever, if it equals our CPU addition result, which we did from way up here, right? It was our simple accuracy check. If the two values match, then the device result matches the host result. If it doesn't match, then we say so. Okay, and then of course we reset the GPU and we're good to go. Website CUDAeducation.com, Twitter, guys, subscribe. Also consider donating. CUDAeducation.com, you can donate to the cause. These things take up resources, so make sure you donate. That's pretty much it. So we know that the device and the host results matches host result. Okay, and that's that. Now we're gonna play with it a little bit. Before you go, what I'm gonna do is I'm gonna take out our little friend right here, sync threads, right? So notice we got this big number here, 127,75676, right? Now what I'm going to do is I'm going to comment out our sync threads. And basically, remember guys, that all that's doing is saying, okay, before you start processing this, make sure this guy is done, right? But I'm going to comment it out, so this guy is just going to keep going regardless of whether these numbers have been finalized or not, right? So I'm going to comment it out and see if whoa, look what we got, a negative number. Device result does not match host results. So you see how dangerous not having sync threads can be? We get a number that's way off, way, way, way off. Okay? Now watch the magic. I'm gonna put back sync threads in. Also, you might want to notice too. The result does not match. I'm gonna put sync threads back in. And see, it matches again. I'm a little curious as to why. I was hoping the time would also change significantly, but it hasn't. But anyway, so I'll do it again for kicks. See, we get a different number this time again. Result does not match. I think the seed of the random generator is always the same. So when we do the sync threads and we do it properly, we should always get the same answer. But when we don't do sync threads, then there's all kinds of craziness happening in the processing, so we always get different answers. So we get this guy this time. Let's rebuild the code and run it, or maybe if I just run it again. See, every time I run it, I get a different answer when I take off sync threads. And it's not because the numbers in the array has changed, it's just because of the way the code is being processed. So I'll do it again. See, get a different number again. I'll do it again. Get a different number again, right? So watch when I put in back sync threads. So regardless of the number of times I do it, when sync threads is on and it's calculating properly, I always get the same answer, right? Which come on. Always get the same answer. Always get the same answer. Take it back out.
Different answer every time. Different answer every time. Because it's basically chaos happening back there in the processing, right? It's just running wild. Yeah, notice how the speed also is a lot faster. Let's see something. Notice how the speed is a lot faster. Let me put back in sync threads, and I'll redo it several times. Right, so we're back up to 115 again. Let me redo it though and see. 103. Let's redo it again. 99. Come on. I don't know what happened that time. Yeah, but yeah, so my theory is that without sync threads, it should run faster than when sync threads is on. But that basically is my conclusion, and you understand the value of sync threads, you understand parallel reduction, you understand moving data from the host to the device and from the device back to the host. You understand how to launch a CUDA kernel, you understand stride, you understand linear address, right? How to get the global location of a thread in all the threads. You sort of get a touch of timing CUDA events. So there's a lot of things you've learned. So this is this is good progress. Okay. And you understand why it's valuable to check that a simple implementation of the code, even though it might be slower, matches the simple CPU implementation matches the value that the GPU is generating. Just appreciate and understand that when you're running things on the GPU, you get threads and you get 20 million of them, and it's very easy if you don't do sync threads properly or in the right places. It's very easy when you're programming with so much parallelism and so many threads that to get things synced up incorrectly and to get values that you didn't mean to get, or adding values that hasn't been properly processed. All right, so CUDA is very powerful. It's all about speed, but you have to really think things through before you actually, press the go button. And you have to check your results. Heavily check every iteration, every permutation of all your trials to make sure that what you think is happening on the GPU is what you want to happen. All right? Anyway, guys, subscribe to my channel. All right? I got to build this up and donate to the cause. I'll even show you. Look, right here. See, you could donate. See, donate. See, it's not gonna bite you. It's not gonna bite you. I promise you, it won't bite you. So you could donate to the cause and get things going. I'll even press the button for you. right, guys, have a good day. Thank you for watching.